Hello everyone, welcome to this lecture on statistical physics. Today we're going to discuss the Bose Einstein condensation in an ideal Bose Einstein gas. So what we're going to do is we're going to consider an ideal Bose Einstein gas. So what this means is one, the bosons are non-interacting. Okay, so these are non-interacting particles. This simplifies the problem quite a lot. And two, that they are bosons, that it's made up of bosons. Okay, and we're going to be interested in what happens in the low temperature limit. Okay, so let's recall what the basic thermodynamic functions work out in the grand canonical ensemble for Bose Einstein statistics. So recall, and this we went through quite a lot in detail during the previous lesson on Bose Einstein condensates. So this is just a review that the number of particles can be written using the density of states, can be approximated using the density of states as this, right? This integral right here. And for the specific case of these non-interacting particles, the density of states takes a form which is proportional to e to the square root of the energy. And so we get v over 4 pi squared 2m over h bar squared to the power of 3/2 integral of e to the 1/2 over e to the beta e minus mu minus 1 dE. Okay. Now, again, what we can do is set x to be equal to beta e and set z to be the fugacity. Then this integral turns into fairly nice form. So again, v over 4 pi squared 2m over h bar squared to the power of 3/2. Now we're going to get a beta 1 to the power of 1/2 from here, and then another power of beta from here, right? But it's going to be 1 over that. So it's going to be 1 over beta to the 3/2 integral of x to the 1/2 over z to the minus 1 e to the x minus 1 dx. Okay, and this integral, well, what is run through, we're going to suppose that we can always shift the ground state, right, as long as we shift all the other states together with it. So I'm going to set the ground state to be 0, so the energy is going to go from 0 to infinity. Okay, and this also implies that our chemical potential will be less than 0. Okay, this is the requirement that we must impose in order for the sum in the Bose Einstein partition in the Bose Einstein statistics to converge. Okay, so side note, a fairly important one though. Okay, so from 0 to infinity. Now this is a Bose Einstein integral, right? So this is equal to gamma of 3/2 g of 3/2 of z, right, where g is a Bose Einstein function. I'm gonna make a video on that fairly soon. I've done one on Fermi dirac integrals and the treatment is identical. And this gamma 3/2 is, I believe, square root of pi halves. And so it's going to simplify with all this clutter right here, and I'll let you do the algebra. The end result is that this is equal to v over the thermal wavelength cubed times, I'm going to write out the Fermi, the Bose Einstein function in full. So the sum from 1 infinity of z to the power of m over m to the power of 3/2. Yeah, that's it. So this is g to the 3/2 z. Okay. Alternatively, another way to put it is the particle density n over v is equal to g 3/2 z over lambda cubed. Okay. Now, next what we want to do is look at the very low temperature limit of this expression right here. Okay, so the low temperature limit is equivalent to, so low T, right? This is equivalent to saying that Z approaches 1, or also that mu approaches 0 from the negative real axis. This might sound counterintuitive because low temperature means beta large, right? So beta to infinity, and Z is equal to e to the beta mu, and so e to the minus infinity, this should go to 0. But this is not true. Not true, because as one can check, mu actually drops to 0 more quickly. Is it gonna fit? More quickly. So the end result is that even though beta does get very, very large, mu drops off more quickly. So beta drops linearly, while mu, I think, drops to the power of 3/2. So, sorry, to the power of minus 3/2, right? So I think mu is t to the minus 3/2, while beta is t to the minus 1. So when you, sorry, plus 3/2, I think. Yeah, that's it. But either way, the end result is that the low temperature limit is equivalent to having the fugacity go to 1. Okay, so what we're going to do is to investigate this low temperature behavior. I'm going to take a sample of this gas, and what I'm going to do is I'm going to keep it at constant, so thought experiment. We take a sample of this gas, take a sample of density n. Okay, next what I'm going to do is I'm going to, at fixed density, at fixed n, I'm going to decrease temperature. Okay, so T to 0. Okay, let's think about what happens. Well, so n is equal to g 3/2 z over lambda cubed, where remember lambda contains a 1 over t to the 1/2 factor. Okay, so lambda is t to the minus 1/2. So as temperature decreases, what will happen is t goes to 0, so lambda gets larger. Okay, so t decrease, but lambda increases. So if we want to keep this left-hand side constant, then we need g 3/2 z to also increase to counteract the fact that the Fermi wavelength is increasing. And luckily we can do this because if you plot this function right here, the Bose Einstein function, what you get is something like this. So remember, the fugacity only goes from 0 to 1, okay? And the behavior that you're going to see is something like this. So so it's gonna start at the origin, right? Let's change color, let's do it in blue. So we're gonna start at the origin, right? And it's gonna do something like that, roughly. It should be steeper, actually. Yeah, that's better. That's more or less what it's going to look like. Yeah. I'm a perfectionist. Okay. That will work. Okay, so this is g of 3/2 z, right? And z is is right here. So we have this right here. This does not go to infinity, but it goes to I think it goes to the zeta function. That's right. It goes to the zeta function, zeta of 3/2. Okay. So what this means is, remember, as t goes to 0, we made this discussion that z goes to 1. So z goes to 1 increasing, and since z goes to 1, z is increasing, right? So this is t lowering. We're going to find that the numerator here increases. So that's good, because the numerator increases, the denominator increases, things stay constant. However, temperature could technically go to 0, right? But this g over 3/2, look, it's bounded above. It's bounded by this zeta function. So at some point, this numerator is not going to be able to compensate for the denominator increasing anymore. When this happens, we get a very interesting phenomenon. We get a Bose Einstein condensate. So let's look at this more clearly. So when does this occur? Well, this occurs when we hit this point right here. When we hit this point where the numerator is bounded above, we're not going to be able to, according to our calculations, lower the temperature further, right? So when does this happen? So for a given density, this happens when z is equal to 1. Okay, so when we reach this point right here, when we reach this point, we get lambda, call it critical cubed, because it's the temperature that's critical. And well, this is equal to zeta of 3/2 over something which I won't bother writing down because I might get it wrong. Something times temperature to the minus 3/2, right? The critical temperature. This is the important temperature we're interested in. Okay, rearrange this and figure out what alpha is, and you'll soon see that Tc is equal to 2 pi h bar squared over mkb, boring stuff, and then n over zeta of 3/2 to the 2/3. Okay, so the important point is that Tc goes as the temperature, as the density to the 2/3. Good. So what happens if we try to further decrease the temperature? Okay, so if we try to further decrease the temperature, this is going to get larger. There's no way this can get larger. If anything, as we'll see, it stays constant, but it can't increase more than what we currently have. That's just how this function works. So it seems like, according to our theory, we can't go below this temperature, which experimentalists will say is a ridiculous thing to say, and indeed it is quite ridiculous, because our calculation is wrong. Okay, and we made a mistake quite early on, which is a horrible thing if it happens during exams, for example. Where did we make our mistake? Well, we made it right here, the very first step. We said, well, the number of particles can be written as this integral right here. And that's true, except this integral does not take into consideration one important state, the ground state. Because for this value, the density of states, well, it's 0. But we know that the ground state has some occupation, so there's not going to be contribution to the thermodynamic quantities from the ground state if we use this integral approximation. What is the correct way, therefore, is to explicitly add a term which takes into account the ground state. Okay, so what does this mean? This means if I go down, this means that in reality, so correction, GS is important. Okay, so in reality, n is going to be equal to the whole integral that we had. So integral of GE over e to the beta e minus mu minus 1 dE, right? Plus the occupation of the ground state. And what's that? Well, you just set the energy to be equal to 0 in the Bose Einstein distribution, and you find that that's just 1 over z to the minus 1 minus 1. And yes. Good. So in other words, we evaluated this integral, right? So n is equal to v g 3/2 z over lambda cubed plus, and I'll rewrite this in this way, z over 1 minus z. Okay? And in the next lecture, we're going to really go through this calculation, and we're going to do some extra calculations using this correct expression. And we're going to see that some very interesting things happen. One last thing that I would like to mention is about the density of excited states versus the density of the ground state near the critical temperature. So we have our expression for the total number of particles, and this is, so this term right here is the number of particles in the ground state, and this right here is the number of particles in the excited states. And because we're working in the thermodynamic limit, v goes to infinity and n goes to infinity, so it's much more helpful to look at the ratio of the occupations rather than the occupation numbers themselves. Let's look at the density of the ground state, or better, the number of particles in the ground state over the total number of particles. If we're above the critical temperature, right? Well, using this expression, we know that z over 1 minus z is going to be finite. So z over 1 minus z is finite for t larger than tc, because z is less than 1. So in this case, this is a finite number, and when we divide by n, the end result is that we get a vanishing contribution. So we just get 0, okay? However, if we are below the critical temperature, then this number is no longer finite, it diverges. So it does make sense to look at this quantity right here, and we see that it is equal to 1 minus v times zeta function of 3/2 over n times the critical wavelength cubed times the critical wavelength cubed over the actual wavelength cubed. So what I've done is here, technically I should have just had the thermal wavelength cubed, but I put in the critical wavelength to simplify matters. because we know that this goes to 1. That's how we derived the critical temperature. And so because this is equal to 1, the end result is that the number of ground states and the number of particles in the ground state over the total number of particles is equal to 1 minus T over Tc to the power of 3/2. Okay? And this is the plot. So we can see that the number of excited states starts to, the number of excited particles over the total number of particles starts to decrease after we lower beyond the critical temperature, while the number of particles in the ground state over the total number of particles starts to increase. Okay, and at absolute zero, of course, we find that all particles are in the ground state.